This is Louis. I wanted to give a quick presentation on a couple of tools that I've been using recently to solve real-world puzzles. I got started on this last month by a friend of mine who he posted a logic puzzle, and I used to solve them with pen and paper, but I wanted to get better at doing it quickly with Python. And I showed a few people, they were interested, so I wound up making a presentation on it. And I released a bunch of open source stuff, including a Jupyter notebook. This is kind of a cross between PowerPoint and an environment where you can run code, so you're not just looking at slides, you can actually run the code. I'll give a link to how to get this. Installation's pretty simple. I'm doing this in Linux. I've successfully done it in Windows also. So installation instructions: you need to have Python installed and pip, which is basically how Python adds additional libraries. We use 3 libraries. We use one for Jupyter Notebooks. We use one for a tool called a Constraint Satisfaction problem solver. And then we use a third library called Picoset, which is more in-depth. In Windows, it's a little bit of a pain in the ass. You need to install Visual Studio and Visual Studio build tools, as well as run this as administrator. Just the first time, so that when you build Picoset, you don't have any problems. But I've got it working in Windows also. So after you've installed everything, you should be able to just run Python-m notebook. What this will do is this will start Jupyter server, our Jupyter Notebook server, and you will see my presentation. All right, so my friend, shout out to Randy Sticky, he posted a simple puzzle. So basically you're given somebody's luggage that has one of those 3-wheel locks on it, and you don't have the lock. And you've tried a couple ones, none of them are right. So if you try 891, you know that one of these digits is correct but wrongly placed. 695, you know none of these digits are correct. And 3 other examples here. And your job is to figure out, what is the code. And you can do this, it doesn't take terribly long with a paper and pencil to get an answer. But like I said, I wanted to get better at doing it with Python. And so my initial strategy was, I don't want to write really rules of how to solve it. I want to instead describe what good and bad solutions look like, and then have my code try all the solutions, which is not terribly hard. So this is the Python for it. If you haven't used Jupyter before, you just click on one of these code blocks to open it, hit Shift-Enter, and it will run. And basically this is a Python function that it'll guess a number. I give it a number and it'll see if it breaks any of the rules. And I've tried to state this as close to English as I can. So from the problem statement, 695, nothing's correct. So I've shown that as a list because order matters. So my disallowed is 695. Here's a list of lists showing the 3 guesses that had something correct but misplaced. And here's my one guess that had a right answer in it. So basically, it'll take whatever number I give it, and we'll check to see if it fails any of these checks. If it contains a 6, 9, or 5. It should contain at least one number found in all of these, but not in the same places, and it should match something in this one. And so, for example, I could check my guess of 100, and it'll say false. And I could check, 121, false. I could just do this by guessing. For this one, I'm just going to make a simple loop and say, look, there's only 1,000 different possible options, because it goes 0 through 9, so 000 to 999. Let's just try them all, and let's find out what the answer to the puzzle is. And it turns out there's like 10 answers, which is kind of funny, because most people, when they're doing it by hand, they find the first solution, and they're just like, cool, this is my solution. But there's actually 10. And this wasn't too hard. It took me about 20 minutes of coding to get this up and running. And it works, but it only works because this is kind of a tiny toy problem. For this problem, like I said, there's only 1,000 possible solutions, so you can brute force it. You can go through and hit them all. In general, the size of your problem space is the product of all of your variables. Here there are 3 variables: the first row, or the first digit, the second digit, and the third digit. of their domains. So they had a domain size of 10 because they could be 0 through 9. So 10 times 10 times 10 is 1,000. So that 1,000's pretty easy. You can do that in microseconds. But I wanted to get better at all kinds of puzzles, including ones that are too big to scale. So like the next example is something that I solved this a while back, but it had been a few years. So I was like, well, I should be able to solve it faster now. So what if you're not dealing with numbers? And what I have here is an image of a Cracker Barrel puzzle. If you go to the restaurant Cracker Barrel, they'll have these solitaire puzzles where there's these little pegs. And the idea is you jump like checkers. So in this one, there's 2 missing. So I could jump this yellow one over here, and then I take out the red. Or I could jump this yellow one to the left and take out this red one. There's basically 4 different possible motions, valid moves that I could do from this initial starting position. The way you play the game is you have 1 missing, and your job is to jump until there's only 1 left, and you don't really care where it is. But as long as you have 1 left at the end of the day, you've solved it. All right. So there's not really numbers here. I don't see anything that easily looks like a number. So I've updated my paradigm a little bit, and so I don't want to write rules for how to solve the problem. I don't want to write strategies of, I'll try outside, try corner pins first. No strategies like that. What I only want to do is I want to describe what the first state of this puzzle looks like, the puzzle when there's only 1 missing. This is the important part. I want to describe rules for how to figure out what my valid moves are, how I can get to my next state, and what the valid next states are. I want to describe what success looks like, and in this case it'll be there's only 1 pin left. And then I want to let the solver explore all the states until it finds success, and then report to me not just that you found success, but go back and show me all the steps you did to get from initial to the final state. These are an example of a class of problems called depth first or breadth first search problems. And if you think of the puzzle as a graph, this top node here, this A, would represent your starting puzzle, where you've only got 1 pin gone. And this diagram only shows 2, but in my puzzle, if I start with this, there's 4 valid moves here. And so my graph would have 4 second tier nodes. And the idea is each one of those would represent, well, if I had jumped this first pin, or I jumped this second pin, and then each one of the corresponding ones, if the arrow points to a different node, that means this is a valid state. You can get here by jumping a pin. And the further down you go, the more pins you've taken out. So the only difference between these is a depth first search will try its best to solve it the first time, maybe with a stupid rule like always try to jump the leftmost. And when it doesn't have any more valid moves, it'll go back and then go 1 more up the chain and see if there's any valid moves it can try from there. So it'll always try to solve first and then kind of work its way backwards. Breadth first will evaluate all of its first options, and then it'll try the first. If that's not a valid end state, it'll start evaluating all of its second moves. In this case, it doesn't make much sense to do it this way. The way this game's played, every move removes a piece from the board, so you're not going to have a good state until you've removed 14 pins, or 13 pins, actually. So these are 2 different search strategies. Both of them will get a right answer. Just for this particular puzzle, breadth first would be much slower. By the way, I wanted to shout out to a talk that I watched and took copious notes from. I thought it was fantastic. It's Raymond Hettinger's PyCon 2019 talk, and basically he describes what I'm describing here. He actually gives a really cool framework for solving this kind of puzzle. I'm going to give a link to this, and then I used his framework for general purpose puzzle solvers to solve this particular triangle solitaire. I'm going to show it working first, and then I'm going to describe what's happening here. This is his code. I'll do a quick walkthrough, but it's remarkably clean and remarkably short. This is all you need to describe how to do a depth first or a breadth first search. So I'm going to run the code, and this doesn't output anything, but what it does is it means that I now understand what class puzzle is. And so here's my code for actually solving the triangle solitaire puzzle. And so I've defined what the initial position is, and I'll explain this a little bit more in depth in a second. But you can see this kind of resembles the triangles where a 1 is a pin in place and a 0 is not. So I'm starting with a puzzle with this last row missing 1 pin. I've defined isGoal, which is, this is a function that says basically count all of these and add every number you see in this list of lists. And it should be 1. If it's 1, then you've solved it. And here's the complicated part. This iterator is showing, okay, given my current state, how do I know what my next possible moves are? And we'll talk about iterators in 1 second, but let's just show it working. And so I start from the puzzle where there's 1 pin missing, and it found a solution remarkably quickly. And it doesn't have a human readable version, but you can kind of see, starting from here, here's your next state. All right, so I obviously jumped, what did I do? I jumped this one, what did I do? I jumped this one over to here. And that's, now I have 2 missing here. And then the next one, I'm jumping this guy, and now I've gotten rid of 3 on the bottom. Go down here, and you find that I've found a solution where the only pin left is this one, kind of in the 3rd row towards the end. What's neat about this is I could define success completely differently. I could actually, I believe I can do this. I'm going to comment this out, and I'm going to say, hey, I have a goal state I want to get to. And my goal will be all zeros. I want, now in this case, I actually care which one's 0. Okay, so now I have a goal state. And so now I should be able to rerun this. And sure enough, it solved it in a different manner. Because I told it, hey, I now want my goal state to have this particular one be the one that's left. And sure enough, it resolved it. And the final solution is different. Before, this one was the pin that was there. Now this one's here. I'm going to take a minute just to talk about how clean Hettinger's... Hettinger he's a maintainer of the Python language itself. So he's a really solid coder, and I was blown away by how simple this is. Basically, this is a class, and you override its starting position. There's 2 different ways you can tell it what a goal is. You could do like I did in the second case, where you give it a literal and say, hey, if your status matches this, you're done. Or you could define a function and say, hey, if this function ever returns true, then we found a solution. And if you don't override it, it just asks, is your current position equal to the goal? This is kind of cool. So depth first and breadth first searches. This is using a component from the standard library called DEC, which is double-ended queue. This comes from collections. And what this is a double-ended queue. So this is a data structure where I can put objects on either the front side or the back side of the queue. And what's interesting is, as I iterate through my triangle solver, what will happen is it will evaluate my state. It'll say, how many valid moves from here do you have? And if I've said I want to do this in a depth-first manner, it'll append these to the end of the queue. And so any of my new solutions will be on the end of the queue, which is also where I'll pop them off when it comes time to check them for whether they're correct or whether I have to go further. Or if I say, hey, I'm doing a breadth-first search, it'll actually append these to the front of the queue. And this is remarkably clever. This means that basically every time I evaluate my current state to say how many new moves do I have, either I say I'm going to evaluate these now or I'm going to evaluate these later. And it's just a real simple logical switch to determine whether I'm doing a breadth first or a depth first. canonical here, this is something that takes advantage of symmetry. If you override it, so for example, if I was solving tic-tac-toe, there's symmetry there. You know, if I play an X on the top left, it's really kind of the same as the bottom left or the top right. And so what you can do is, if you can find a clever way to transform your current state to get rid of symmetry, you can have it take less room in memory as it's searching here. Yeah, and iterators, these are cool. So what an iterator is basically, this is a function in Python that if you have it defined with this dunder iter here, then basically you can put it in a for loop, and it's like, hey, here's the logic for if I put this in a for loop, how do you give me the next item in this loop? When I defined it here, this is really the brains of my triangle solver. This is basically saying from your current position, so starting with this, you have a couple of different directions that you can do jumps in. And so every time I loop through and ask for a different one, you know, check and see if you're doing a left jump, if you're doing a right jump, if you're doing a jump down, if you're doing a jump up. And these are this is basically the logic for, you know, how do you find out what your next valid move is. And every time, this is a generator, so every time this iterator looks for the next thing to return, or actually yield, it gives a new instance of the same class. This is class Triangle Solitaire. It inherits from puzzle, which this is what Raymond Hettinger created. And all I'm doing is I'm creating a new instance of this class with the new position. And so that's pretty tight. This repr here, this is basically having it print in a pretty state. So when I solved it, it's printing in these pretty sort of triangular looking outputs. If I didn't have that there, it would just print a list of lists all on one line and it would be ugly. So yeah, this is my triangle solitaire solver. If you go to his talk, he gives a couple of his own examples there. They're really cool. Like some of them are logic puzzles, like you have 3 different sized jugs and one has water in it, the other ones don't. How can you mix the water so that you wind up with a jug that's only got 4 liters in it? He's also got some interesting sliding tile problems that can be solved with this manner, with this approach. And the reason this approach works is because the nature of this puzzle is that there's a limited number of moves from every starting position. There's cases where that's not true, and here's a good example of one. So this is, going down here, this is Sudoku. Sudoku is a puzzle, and this type of puzzle does not work well with depth first or breadth first searches. And if you think about this, take a look at this puzzle for a second. This is an 81 array. This is an 81 element matrix. It's 9 by 9. This is its initial starting state. Its next state, meaning I'm going to choose some number to put in one of these, there is a tremendous number of options. So my last puzzle had 4 options. I haven't calculated how many are in this particular one, but in general, like if I had a completely blank Sudoku puzzle, there are about 2 times 10 to the 77th different possibilities. That's like 1% of the atoms in the observable universe. Big ass number. This is not something we're going to have any luck brute forcing. So we need a completely different approach. And the approach we're going to use for this is a solver called a constraint satisfaction problem solver. And this is kind of cool. So we're still not writing rules for how to solve Sudoku. When I was first learning, and I got this, my daughter's got a book on this, she loves Sudoku. When I was first learning, you'd say, look, this row here has, it's only missing 3, so we'll start there. I'm not going to put any strategies in on how to solve Sudoku. All I'm going to do is I'm going to give it the initial Sudoku puzzle. I'm going to describe basically how to play Sudoku and describe the variables, which in this case, each of these numbers is a variable. If the number is already given to us, it's a variable that's known, so it's got to be 5. But this one is a variable where its domain is could be any number from 1 to 9. So it's got 9 different possibilities in its domain. So basically, I define the variables, I define the constraints, and this is The constraints for Sudoku are all the numbers across have to be different, all the numbers down have to be different, every one of these 3x3 matrices has to be different. And then I let the solver figure out how to get from here to there. This is called a constraint satisfaction problem, or CSP. Let's see how to do that. This is my initial puzzle, and I've chosen to put zeros in here. This makes it easier to read. A zero means I don't know what the value is. So you can see on here 00530, and that corresponds with blank blank 53 blank. Zero basically means you have to figure out what the true number is. But the idea here is I want this is a list of lists, and each list is a row. I want this to match the original picture of the puzzle as closely as possible, so it's possible to get like intuition about what's happening. So I describe the 81 variables and their domains. And this is, I'm using a library called Constraint. When you installed this Jupyter Notebook, it installed Constraint along with the Jupyter Notebook. This is a third-party library for Python. And basically the idea is we go through here and we say, look, I'm going to save a variable for each of these 81 numbers. If the variable is 0, let's see, if the variable is not 0, then I'm going to say your domain is just this number. So if I come across this variable, or this variable, I know its domain is only 5. But if I come across this variable, its domain is the numbers 1 through 9. And that's what this part's doing here. So let's run this. Let's run this. Again, there's no output. This is just defining the problem. Let's describe the constraints. And these are the rules for how to actually play Sudoku. This is the rule that says, hey, everything in a row has to be different. This library has an optimized function called add constraint. Here's something interesting. So this line here, this is basically saying I'm adding a constraint saying that they all have to be different in a particular row for every column entry in that row. This is logically equivalent to it. This is using a lambda expression. But this is using just straight Python, and this is using the constraint optimized library, which is probably C with Python bindings. If I do it my way, I do get an answer, but I have to wait a really freaking long time for it. Like, there's 27 constraints here. If I replace 6 of them with this, it can do it in about 10 seconds. If I start replacing 7 or 8, now it's taking minutes. If I replace 10, it takes hours. So this runs into this is useful for illustrating. Sometimes having the right answer isn't enough. You also have to do it quickly. And so I'm making use of their optimized functions for helping me. This is constraint 2. This is all of your columns have to be different. And this is the constraint for making a 3x3, all the 3x3 matrices, all 9 of them, be different. And so this is kind of cool. All I'm doing when I solve it, I'm going to take a snapshot of the time before I do the solver. I'm just going to say, find the solution. I'll take a snapshot of the end time, and I'm just going to print the result. It took less than 0.03 of a second, and it output the Sudoku output here. So I could easily change this around for any Sudoku problem. We tested it with about 6 or 7 in her book, and even the hard ones, it takes milliseconds. Super fast. The cool thing about this is I'm using a third-party library for doing constraint satisfaction. These things get better all the time, and so I'm solving an 9x9 Sudoku problem. You could have a 100x100 Sudoku problem, and these libraries keep getting better and better. And the idea is that my code remains stationary, but by using better libraries, I can do more powerful things. This is kind of the next level. This is SAT solvers. You could have, the SAT solvers are a cool class of solver. We're going to use, I'll explain what SAT means and all the buzzwords in a second. But you guys have seen puzzles like this. These are logic puzzles. They call this the Einstein puzzle. And this is something I took directly from Raymond Hettinger. But there are 5 houses, each with its own color. There's 5 different people, one lives in each house. There's 5 different drinks, 5 different cigars, and 5 different pets. And then they give you a whole mess of rules, like, oh, the Brit lives in a red house, the Swede has a dog. And you have to figure out something like, well, who keeps the fish? Everyone's seen these, and I think if you passed 5th grade, you can do these on the back of a piece of paper pretty quickly. 10 minutes, probably be enough to solve it. But the idea here is, this is like 30 variables, 5 houses, 5 colors. What if you had like thousands of each? And CSP solvers, we're going to use one called Picosat, which is written in C and has Python bindings because it's heavily optimized. This thing can handle hundreds of thousands, if not millions, of variables. So you can handle very, very complicated problems. They have to be logic problems. This does not deal in numbers. It only deals in Boolean true or false logical statements. And so let's talk about, we call this a SAT solver. That means satisfiability in a Boolean sense, meaning true or false, yes or no. Satisfiability just means, can you find at least one combination of inputs that makes a statement true? And so SAT solvers are super powerful, but they're kind of weird in that you have to specify your the problem in a very particular form, and it's called conjunctive normal form. The idea of this is it's basically one and statement with a whole bunch of or clauses, ors and nots. In conjunctive normal form and prepositional logic, escape from there. Conjunctive just means a Boolean and normal form just means this is agreed upon. So here's an example. Here's a English logic statement. If the tire is flat, then I will have to remove it and take it to the gas station. So in order to use this in a SAT solver, I have to state this in conjunctive normal form. And this line is equivalent to the statement, the tire is not flat, or I need to remove it, and the tire is not flat, or I need to take it to the gas station. So both of these mini statements are clauses. They only contain ors or nots in them, and all of them have to be true. They're all anded together. If you've taken a propositional logic class, the syntax might be familiar to you, where this symbol here is a not, and this is an or, and this is an and. So, very strange way of stating a problem, but if you can get a problem, a Boolean logic problem, into this form, you can solve it with a truly stupid number of variables. Let's see how we do this. So here, we're using Picosat. So Picosat has a pretty terse syntax. Raymond Hettinger created some helper libraries to make it a little bit simpler. Here we're defining the houses and the groups and colors. This matches directly this. And what we're going to do is we're going to create this conjunctive normal form. This is going to be a list, and every element in the list is going to be a clause of things that are ORed together. And so he's made some helper functions. So, for example, these rules here. So we're going to add a clause that says, same house, Brit, red. This is close to the same English as the Brit lives in a red house. And the idea here is we want to make things match the human language, the natural language of our problem as closely as possible. I'm going to run this, and here's the output. And it found it's a satisfaction problem. So it said, is there any combination of inputs, and there's 30 inputs, that results in a true statement? And the true statement it's evaluating is this conjunctive normal form. And it said, yes, here is the list of inputs that can be true, that result in a true statement. So Norwegians in house 1, yellows house 1, cats house 1, waters in house 1, Dunhills in cat house 1, and so on. What's interesting here is, if I say, let's take a look at this CNF. This is the propositional logic that it created in order to solve this problem. And it's, at first glance, it's really strange looking. It's huge, first off. like it's big enough that it's not even going to show me all of the clauses that it put in. There are 1,100 clauses that it put in just from the problem statement. So putting something in a conjunctive normal form is going to make it very verbose. But let's look at this. Like the first clause says, not Dane 1, comma, not Brit 1. These are evaluated as or, so all of these have to be true. So it has to be a true statement that not the Dane is in house 1, or not the Brit's in house 1. Also, not the Dane's in house 1, or not the Swede in house 1. This is basically a really weird logic way of saying that a house can only have one person in it at a time. And so this is a way of writing, hey, a house can only have one person in it at a time. And Jupyter Notebook limits these cells, or you won't be able to see it all, but this is all of the logic statements that you have to put in order to get one statement in conjunctive normal form that this picosat solver can satisfy. But it's incredibly powerful, and it scales up to hundreds of thousands, probably millions of variables. This was only like 30 or 35 variables. All right, I wanted to share this because I find it fascinating, just finding fun, fast ways to solve logic problems and number problems using Python. If you have any questions, let me know. I'm going to include a link to basically how to get this repository. It has a README in it, so I'll shut down my Jupyter Notebook server, and this has instructions. The README has instructions for basically how to get started, and then how to run it. Once you run it, you'll get a link like this to your local host. So it's running on your machine, and you can run the code to your heart's content. Modify it. Let me know if you find it useful, and hope you guys have a great day. Take care.